Hello everyone. Here is something that will change how you look at every car, every robot you ever see again. When a car turns a corner, as you can see here, the front left wheel and the front right wheel, they are turning at two different angles. You can see delta L and delta R are having two different angles whenever the car is taking a turn. Not the same, they have to be the different angles always. And if they were not, if I show you, in this case you see they are not turning, they are turning here in the same angle. If you observe this, the angle is same. So in that case, what would happen? The tires would scream, rubber would scrub sideways across the road, and your steering would fight itself to death. So who decides the angle? Who calculated the exact difference? Was it a computer, a modern algorithm? The answer is no. It was a man named Rudolf Ackermann in 1818 for horse-drawn carriages. And the geometry he used was pure triangles and trigonometry, which is sitting inside every self-driving car on earth right now. You can see here. So now let's get to the core problem. Why one angle is never enough? Let's build the intuition first. You can watch this simulator here. I'm going to steer both the wheels to the exact same angles, which is called as the parallel steering. So let us see what happens. In this case, you can see those two red crosses on this screen. Those are the two different centers that each wheel's axle is pointing towards. Now two different rotation center for one rigid car. Car cannot rotate in that case around two centers at once. So in that case, the tire gets dragged. That's the tire scrub. That's basically the wasted energy, wasted rubber, wasted everything. Now I switch to Ackermann mode. In this case, what is happening is four different color perpendicular lines you can see here. One from each wheel, and they all meet at the same single point, one point, at the ICR, which is the Instantaneous Centre of Rotation. The car has exactly one rotational pivot at every instance whenever it takes a turn. That's not a coincidence, that geometry enforcing physics. Now, where does the ICR have to live? Think about the rear wheel first. Let us see what is happening with the rear wheel. So, we know that the rear wheel cannot steer. Their axles always point sideways perpendicular to the car. So the ICR, which is the Instantaneous Centre of Rotation, it must sit somewhere along the extension of the rear axle, which you can see here. Along the yellow dotted line lies that ICR. Now the front wheels must both aim at the same point because of the same angle. They must aim at the same point, that is ICR. Each one forms a right triangle with the car's body. If you can see here, both the wheels of the front, they are forming a right angle triangle each with the body of the car. Correct? Like if we see the left front wheel, the blue dotted line, the yellow line, and the body of the car acting as a base, it is forming a right angle. So both the wheels are forming right angles with the body of the car. That's all. Capital L, which you can see all the live values you can see here. So capital L here is nothing but it is the front axle to rear axle. What is the distance? That is called the wheelbase, capital L. And track width is the width of the track on which the car is moving from left wheel to the right wheel. That is the distance, capital T. And turning radius is a capital R, which is the rear axle center to the ICR basically. Now from there we calculate what is the tan of delta. Tan of delta is basically nothing but capital L over capital R. Correct? the wheel angles is the delta. So basically it is calculated by L over R. Now let's get to the Ackermann's equation. 2 wheels, 2 angles, 1 formula. Here is where it gets elegant. The inner front wheel, if you see, is closer to the ICR by half the track width, and the outer wheel is further by the same amount. Correct? That means if I see this delta R, or you can see this red wheel which is towards left, that is more closer to ICR, that is the center of rotation, and the blue wheel which is in the front, it is farther from the ICR by what amount? By capital L. Correct? Now, so we write the triangle formula for each wheel separately. So if I write down for this delta R, what you are going to get? For each wheel, if we see, what we are going to get? Tan inverse of L over R minus D over 2. This is what we get. R minus D over 2 is nothing but the distance to ICR for each front wheel, and similarly for the right wheel. So delta in, delta out, we calculate like this. Now, if we take the cotangent of both the equations, we are going to see what happens. R will disappear completely. The turning radius cancels out, and we are just left with cot of delta out minus cot of delta in is equals to capital T over L. Track width divided by the wheelbase. That's the Ackermann condition. It depends only on the car seat, not the speed, not the radius, not the road. Whatever you do with the sliders, this identity will always hold. Let us increase the speed. You change the turning angle. You can change the wheelbase, change the width of the track. Every time this condition, the Ackermann's equation is going to be held. The equation is cot of the angle of the outer wheel minus cot of the angle of the inner wheel is always equals to capital T over capital L. So that's what drives all the modern vehicles. Now here is a jump to robotics. Engineer collapse all 4 wheels into a single virtual front wheel, which is called the bicycle model, and the car's position and heading update every moment by 3 equations, and you can see those 3 equations here, which is the car's position at any instant is described by 3 parameters, which is the x value, y value, and the theta. From there we are getting these 3 differential equations, which is x dot, that is the velocity in x direction is v times cos theta, in y direction it is v times sin theta, and the turning angle is v over L times tan of delta. Correct? And since the body is not just translating, it is rotating as well, that we can see here. Correct? It's rotating. So in that case, about the ICR, it is rotating. So circular motion kinematics also applies, and we have studied these formulas. Omega is v by r, s is r times delta theta, and the acceleration is v square over r. So those are all related to circular motion. Correct? Angular velocity, centripetal acceleration is what we call as AC. The car on a screen computes both live. You can see here. If I drag the wheelbase slider to maximum, let us see what happens. The car corners, it becomes wider. You see, as I decrease the base, and what happens when I increase the wheelbase? In that case, the car just corners wider like a bus. Same steering angle, just bigger L and bigger R. Now maximum tracked wheel, was the inner and outer angles diverge further. If you see at the maximum, they are diverging. Correct? The wider the car, the harder the geometry has to work to keep everything consistent. And if I switch back to parallel steering, let us see what happens. Again, wrong mode. Now you see the trails, if you watch, the wheels are fighting in that case. Watch the trails. The paths don't align as well. The maths broke here and the rubber has to pay the price. Rudolf Ackermann never saw a car. He never imagined a robot as well. He just looked at his horse carriage wheel geometry and wrote a triangle and solved it. 200 years later, every Tesla, every ISRO rover, every warehouse robot, every autonomous delivery vehicles, they uses a variant of his idea. The geometry is so fundamental that the robot doesn't choose it, the geometry forces it. That's the beauty of mathematics. It doesn't care about the century, it doesn't care whether it's a horse drawn carriage or a Mars rover. The triangle is the triangle, the law is the law. Mathematics isn't a tool we use to understand the world. Mathematics is the structure the world is built on.